Have you ever wondered how your computer manages its memory resources? Well, let's dive right into it. Memory management is a core function of operating systems, handling the allocation and deallocation of memory to processes. It's like a vigilant steward, ensuring each process gets the memory it needs and takes back what's no longer necessary. Beyond allocation, memory management is also about isolation and protection, acting like a bouncer that ensures processes don't interfere with each other. It's all about efficient utilization, squeezing as much as possible into memory, while keeping everything running smoothly. Finally, there's address translation, which is like a map that guides processes from the virtual addresses they use to the physical addresses in memory. So you see, memory management is a pretty big deal. It's the unsung hero that keeps your computer running efficiently and securely. An understanding of how memory management works is fundamental to understanding how your computer operates. There are many key concepts in memory management that you need to understand. Let's dive into the first one, physical memory. This refers to the actual hardware memory in a system, typically represented by random access memory or RAM. Now let's talk about virtual memory. This is an abstraction of physical memory that provides an expanded address space and other benefits, allowing your system to run more processes than what the physical memory alone could handle. Next up is memory segmentation. This is the process of dividing memory into segments with varying access permissions. This allows for the separation of code, data, and stack, helping to maintain order and efficiency within the system. Following this is paging. This technique involves dividing memory into fixed-size blocks called pages. It's a key method used to manage virtual memory and reduce fragmentation, making your system run smoother. Moving on to page tables, these are data structures used to map virtual addresses to physical addresses in a paging system. They play a crucial role in address translation, ensuring that each process accesses the correct memory location. Now, let's discuss page faults. These occur when a process tries to access a page that's not currently in physical memory, requiring the operating system to load it from disk. While they may sound like an error, page faults are a common part of memory management. Finally, we have swapping. This is the process of moving pages between physical memory and disk to manage memory overflows. It's a fundamental component of virtual memory systems, helping to ensure that physical memory is used as efficiently as possible. These concepts form the foundation for the various techniques used in memory management. They help to ensure that memory is allocated and deallocated efficiently, that processes are isolated and protected from each other, and that the system makes the most of its memory resources. Understanding these concepts is key to grasping how operating systems manage memory and how they maintain performance and stability. Let's dive into some of the techniques used in memory management, starting with fixed and variable partitioning. Fixed partitioning is one of the earliest and simplest forms of memory management. Picture your system's memory as a block of apartments, each of the same size. In fixed partitioning, these apartments are allocated to processes based on their size. If a process can fit into an apartment, it's allowed to move in. However, if the process is too big, it needs to wait for a larger block of memory to be free. One of the advantages of this approach is its simplicity. However, it can lead to what is known as internal fragmentation. This happens when the assigned memory block is larger than the process it houses, leaving a portion of it unused. Now, let's move on to variable partitioning. Using the same apartment analogy, variable partitioning is like having apartments of different sizes. The memory is divided into partitions of varying sizes, tailored to the needs of the processes. This means that each process gets just the right amount of space it needs, reducing the internal fragmentation we saw in fixed partitioning. However, it's not all sunshine and rainbows. Variable partitioning can lead to a different kind of fragmentation: external fragmentation. This occurs when the memory is filled with small, unused gaps between partitions, which together could have accommodated a new process, but individually are too small. So, in a nutshell, while fixed partitioning is simple and straightforward, it can lead to internal fragmentation. On the other hand, variable partitioning, while more efficient in terms of space utilization, can result in external fragmentation. Both of these partitioning techniques are fundamental to understanding how memory management works. They provide a basis upon which more complex techniques such as paging and segmentation are built, which we'll explore in the next scene. Partitioning is a basic yet powerful technique for managing memory resources. Next up are the techniques of paging and segmentation. Let's first delve into paging. This technique slices memory into fixed-size blocks called pages. Virtual addresses are then mapped to physical addresses using data structures known as page tables. The beauty of paging is that it minimizes what we call external fragmentation, allowing for a more flexible memory allocation. But there's always a flip side. Paging can increase overhead due to the management of page tables, which could lead to slower access times. Now, on to segmentation. Instead of fixed-size blocks, memory is divided into variable-sized segments, each representing different logical parts of a program. These could be code, data, stack, and so forth. Segmentation offers a logical organization of memory, which can reduce fragmentation. However, like every rose has its thorn, segmentation can lead to external fragmentation. Managing segment tables can also become complex, adding another layer of challenge. Remember, these techniques are not mutually exclusive. Many operating systems combine paging and segmentation, using pages as the units within segments. This hybrid approach attempts to harness the strengths of both methods. It aims to achieve the flexibility and reduced fragmentation of paging, with the logical organization and protection provided by segmentation. However, this combination is not without its downsides. The increased complexity can lead to higher overhead, and the risk of both internal and external fragmentation still exists. It's a delicate balancing act that operating systems must perform, weighing the benefits against the costs to optimize memory usage and performance. In a nutshell, paging and segmentation are powerful tools in the hands of an operating system, helping to manage memory more efficiently. They offer a greater degree of control and flexibility than fixed partitioning, but they also introduce their own set of challenges. These techniques require careful management to avoid potential pitfalls and to ensure the smooth running of the system. Paging and segmentation offer more flexibility in memory management, but they come with their own challenges. Finally, we come to the technique of virtual memory. Virtual memory is an ingenious trick that our operating systems use to give the illusion of a memory space much larger than the actual physical memory. It's a sort of memory mirage that greatly expands the horizon of possibilities for our programs and processes. Implementation-wise, virtual memory is a beautiful blend of paging and swapping. It uses paging to divide memory into fixed-size blocks, creating a virtual address space. Then, it employs swapping to move these pages between the physical memory and the disk, effectively managing memory overflow. This combination works wonders in providing a seemingly infinite playground for our programs. It allows larger programs to run and multiple processes to coexist, even if they collectively require more memory than the physical memory can offer. However, like all good things, virtual memory comes with its own set of challenges. One of these is the increased disk input-output operations. When a process tries to access a page that's not currently in the physical memory, a page fault occurs. The operating system then has to fetch the page from the disk, which is significantly slower than accessing it from the physical memory. This increased disk I/O can slow down performance during these page faults. But even so, the advantages of virtual memory far outweigh its drawbacks. The ability to run larger programs and handle multiple processes simultaneously makes it an invaluable tool in memory management. It's like having a magic bag that can hold much more than its physical size would suggest. And that, my friends, is the power of virtual memory. Virtual memory allows us to run larger programs and multiple processes, but it can increase disk I/O and slow down performance during page faults. So there you have it, the basics of how your computer manages its memory resources. We've journeyed through the key concepts such as physical and virtual memory, memory segmentation, paging, page tables, page faults, and swapping. Each of these elements plays a vital role in the intricate puzzle of memory management. We've also explored the various techniques that operating systems employ, including fixed and variable partitioning, and the implementation of virtual memory. These techniques each have their strengths and challenges, and are designed to balance performance, resource utilization, and protection. As the backbone of your computer's operation, memory management is a complex but fascinating field, one that continues to evolve as technology advances. Remember, understanding memory management is essential to understanding how your computer operates efficiently and securely. Until next time, keep exploring, keep learning, and remember that every byte counts.